Hello there, and welcome to a moment of peace. What are the softest sounds you know? Perhaps the quiet rustle of leaves in a summer breeze, the distant hush of ocean waves at dawn, or the soft ticking of a clock in a sleeping house. Maybe it's the gentle sound of your own breathing as you lie in the dark. In this shared moment, let's imagine those softest sounds and allow them to wrap around us like a comforting blanket. Take a slow, deep breath. Feel the weight of the day begin to melt away. As you exhale, imagine you are breathing out any lingering worries or tension. This is your time, a safe, tranquil space for relaxation. You have permission to let go of any rush or responsibility. Nothing is expected of you right now except to be, to listen, and to drift along with the story I'm about to share. Tonight, we will journey far beyond our earthly concerns and into the quiet wonders of the cosmos. Our guide will be the life story of a star, a gentle, glowing beacon in the night sky. From its birth in a cloud of dust and gas to its final whisper of light, we will follow the star's entire life cycle. Along the way, we'll explore how scientists have learned the secret language of starlight, how ancient myths and cultures found patterns and meaning in the stars, and how even in death a star gives new gifts to the universe. All of this will unfold in a calm, soothing narrative designed to ease you into rest. There will be no harsh sounds or sudden surprises, only the slow, steady rhythm of a celestial story. As you listen, you can close your eyes if you like. Picture the vastness of space stretching out above you, sprinkled with countless stars. They have been shining for billions of years, and they will continue for billions more, quietly keeping watch as we sleep. Feel free to let your mind wander among those stars. If you drift into sleep at any point, that's perfectly fine. The story will continue to flow gently, whether you're consciously following along or simply absorbing the calming atmosphere. Just know that you are connected to these distant lights in a very real way. The atoms in your body were born in stars long ago. We truly are made of star stuff, sharing a common history with the cosmos. So get comfortable, snuggle into your bed or your favourite chair. Allow your breathing to find a slow, easy pace. With each breath you can imagine floating a little farther away from your worries and a little closer to the peaceful stars above. Are you ready? Let's begin our journey with a single star twinkling softly, high up in the night sky. Watch it with your mind's eye, shimmering gently. Our story starts there, with that star and all of its stellar brothers and sisters, as we learn how to read the quiet light they send us. Now, let's step into the cosmos together, one gentle moment at a time. Transition to the unfolding story of the star. Hello, and welcome. I'm so glad you're here. Let's find a quiet space together, a place where the world can fade away for a little while, a place just for you, just for this moment. Before we begin our journey tonight, I want to ask you something. What are the softest sounds you can imagine? Perhaps it's the whisper of wind through pine needles, or the gentle lapping of water on a quiet shore. Maybe it's the sound of a cat's purr, a low, steady vibration of contentment. Or maybe it's just the sound of your own quiet breathing in a still room. Whatever that sound is for you, hold it in your mind for a moment. Let it be an anchor, a soft place for your thoughts to land. Now, as you settle in, I invite you to get comfortable. Let your body find the position that feels most at rest. Allow your shoulders to relax, to drop away from your ears. Feel the weight of the day begin to lift, releasing its hold on you with each slow, easy breath. In and out. Let your eyelids grow heavy, and if it feels right, allow them to gently close. There is nothing else you need to do, nowhere else you need to be. Just be here in this moment breathing. Tonight we're going to listen to a story. It's one of the oldest stories in the universe, a story written in light and gravity, in fire and in dust. It's the story of a single, gentle star. We will travel across unimaginable distances, through clouds of cosmic colour, and watch as, over billions of years, a point of light is born, lives a long and steady life, and finally returns its essence to the cosmos in a final luminous sigh. As we travel through these vast clouds of cosmic dust and watch the slow dance of gravity, allow my voice to be a quiet guide, leading you not just through the cosmos, but toward a place of deep and peaceful sleep. There is no need to hold on to any of these words. Simply let them wash over you like the softest of sounds. Let the story carry you gently into the quiet of the night. We begin our journey by playing the role of a cosmic census-taker, quietly surveying the vast family of stars. Imagine drifting through a clear night sky, clipboard in hand, gently counting and classifying the stars by the light they give. Each star's glow carries secrets about its nature, its temperature, its size, its age. By studying the faint rainbows in starlight, astronomers have learned to sort stars into categories, much like identifying species of living creatures in a serene cosmic meadow. The primary tool for this stellar census is the Morgan-Keenan spectral classification system. It uses 7 letters, O, B, A, F, G, K, M, to arrange stars from the hottest, O-type stars, to the coolest, M-type stars. Early astronomers, many of them women working meticulously at Harvard over a century ago, crafted this system by poring over thousands of star spectra on photographic plates. You might remember a mnemonic they invented. Oh, be a fine girl, kiss me, a playful phrase that hides a cosmic order. O-type stars are the hottest, shining a fierce blue-white. Perhaps we can think of O-stars as impatient, brilliant artists. They burn through their fuel quickly, living short, dazzling lives. On the opposite end, M-type stars are the coolest, glowing with a soft red hue. M-stars are like ancient, patient storytellers, slow-burning embers that can glow for tens of billions of years, outliving almost everything else in the galaxy. Between those extremes, each spectral class has its own character. B-type stars are extremely luminous and blue, just slightly cooler than O-stars, often seen as the sparkling beacons of young star clusters. A-type stars shine white. Many of the bright stars you see in constellations are A-class, known for strong hydrogen signatures in their light. F-type stars are yellow-white, slightly warmer than our Sun. G-type stars, like our Sun, classified as G2, are warm and yellow, cozy middling stars that make excellent homes for planets. K-type stars glow orange, cooler and smaller than the Sun but longer-lived. Each type is a kind of stellar personality, whispering its temperature and energy through colour. But a star's spectral letter is only part of its story. There is also the matter of luminosity class, an indication of the star's size and stage of life. Astronomers add Roman numerals to the classification. For example, V, 5, denotes a main sequence dwarf star, one that, like the Sun, is in the long, stable midlife of fusing hydrogen. A 3 indicates a giant star that has expanded and cooled after exhausting its core hydrogen. And I, 1, is reserved for the most luminescent supergiants, enormous stars nearing the ends of their lives. If we add this to our star personalities, it's as if each star has a first name, its spectral letter, and a last name indicating its stature. Our Sun's full spectral name is G2V, telling us it's a G-class star, subclass 2, on the main sequence, luminosity class V, essentially a steady yellow dwarf. Meanwhile, the red star Betelgeuse in Orion's shoulder is roughly an M2I, an M-class red supergiant nearing the end of its life. Such details are like noting that one person is a young adult while another is an elder, the star's age and size encoded in its light. All these stars, plotted together by their temperature and brightness, create a grand pattern known as the Hertzsprung-Russell diagram, or HR diagram. Rather than think of it as a dry graph, let's imagine it as a map of the stars' lives. On this map, temperature runs one way, from hot blue O stars on the left to cool, red M stars on the right, and intrinsic brightness, luminosity, runs upward. When we place every star at the coordinates of its spectral class and brightness, a beautiful sequence emerges. Most stars, including our Sun, lie along a gentle diagonal slope called the main sequence. This is the long, flowing river of stellar adulthood, where stars spend the majority of their lives steadily burning hydrogen. Higher up on the map, veering off the main sequence, we find the giant branch and supergiant regions, where stars swell in old age, becoming hundreds of times larger and often thousands of times brighter than they were in their youth. And tucked down at the bottom left of the chart, there's a collection of faint hot embers, the white dwarfs, small and dim, which are the final stage of sun-like stars after they have shed their outer layers. Each point on this stellar life map is like a milestone marking where a star is in its journey from birth to death. Our stellar census wouldn't be complete without noting that stars, like people, belong to different generations in the cosmic family. Astronomers speak of population 1, 2, and 3 stars, and though the terminology might sound technical, we can liken it to generational eras. Population the Y stars are the younger generation, stars like the Sun, rich in heavy elements, what astronomers call metals, inherited from past supernovae. They have within them the carbon, oxygen, iron and other elements that were forged in earlier stars. Because of this, these are the stars that can form rocky planets like Earth. Population Y stars populate the disks and spiral arms of galaxies where new stars continue to be born. Next come population 2 stars, the grandparent generation. These older stars are metal poor, meaning they contain only tiny traces of elements heavier than helium. They formed in an earlier era of the universe, before many supernovae had seeded space with heavy elements. Population 2 stars are common in globular clusters and in the halo that surrounds our galaxy. They shine with a more primordial light, composed mostly of hydrogen and helium. Picture an ancient globular cluster as an old, luminous city of stars. Its inhabitants are golden red, aging stars that have been burning for 10 billion years or more. They quietly tell us the story of the young universe, their light unchanged by the heavier elements that tint the stars of later generations. Finally, we honour the almost mythical population 3 stars, the ancestor generation of stars. These were the very first stars born after the universe began. They were made of pure hydrogen and helium, without any contaminating heavier elements. Because of this pristine composition, astronomers think population 3 stars grew to tremendous masses, perhaps hundreds of times the mass of our Sun. With such mass, they would have burned brilliantly and briefly, living only a few million years before ending their lives in cataclysmic supernova explosions. Those first supernovae were not an end, but a beginning. They forged the first heavy elements, carbon, silicon, iron, and all the rest up to iron, and scattered them into the cosmos. No population 3 star has been observed directly. They lived in a time so distant and early that their light has faded from view. Yet we see their legacy in everything around us. The heavy elements created by those stars now compose our world and our bodies. Every atom of calcium in our bones and iron in our blood was crafted in one of those ancient furnaces. Whenever we marvel at the gold of a wedding ring or the oxygen in our breath, we are touching the distant echo of the first stars. In this way, through patient observation and a bit of imaginative analogy, we come to see the stellar populace not as an anonymous crowd of lights, but as a family with a rich history. Each star has a story written in its faint glow. Whether it burns hot or cool, whether it is young or old, solitary or one of a cluster, and even which generation of stars it belongs to. For a moment, picture yourself floating gently among the stars of a clear night. You glance around and recognise, here a young blue O-star artist just being born. They're an ancient red M-star sage quietly recalling tales from the early universe. You feel a sense of kinship with these distant lights. Our next step on this journey will bring us closer to the human side of this cosmic story. The people here on Earth who first learned to decode the stars' secrets and extended our senses across the light years. While the stars themselves shine silently in the night, the story of how we came to understand them is also filled with quiet, devoted heroes. Let us drift back about a century to a modest office at Harvard College Observatory. It's early evening, and a soft golden light falls on rows of wooden desks. At each desk sits a woman, carefully examining glass photographic plates that capture the spectra of stars. These women were called computers, not machines, but human beings whose tireless calculations and observations advanced astronomy in profound ways. In an era when opportunities for women in science were limited, they toiled meticulously in the background, yet their findings would forever change our map of the cosmos. In the previous chapter, we benefited from one of their achievements, the star classification system refined by Annie Jump Cannon and her colleagues. Cannon was a quiet, brilliant observer who, starting in the 1890s, examined hundreds of thousands of star spectra. Night after night, she discerned patterns in the faint smudges and lines on those plates, gradually organizing stars by their temperatures. It was her work that established the OBAFGKM sequence we used as our Cosmic Family album. She had such an astonishing eye for detail that, according to legend, she could classify a star's spectrum in just 3 seconds. Cannon and the other women at the observatory, names like Williamina Fleming and Antonia Maury, received little recognition in their time, but they left a legacy written in every astronomy textbook and encoded in the very letters we use to describe stars. Among these Harvard computers was a particularly insightful woman named Henrietta Swan Leavitt. She had a gentle passion for the night sky and a mind keen on discovering order in the stars' changing lights. Leavitt was tasked with studying variable stars, stars that rhythmically brighten and dim over time. On her plate-filled desk lay images of the Magellanic Clouds, 2 small companion galaxies to our own. Scattered across those images were dozens of tiny variable stars called Cepheid variables. Each Cepheid star winked in a steady pattern, brightening, then fading over a period of days or weeks. Leavitt began to measure these periods and compare them with the star's apparent brightness on the photographic plates. In doing so, she uncovered a remarkable relationship. The brighter a Cepheid star intrinsically was, the longer its period of pulsation. This discovery, published in 1912, was like finding a secret key to the vast distances of space. Henrietta Leavitt had given astronomers a new kind of cosmic yardstick. To understand why it's so powerful, imagine standing on a quiet street at dusk, looking at a row of street lamps stretching into the distance. Suppose all the lamps are identical, each putting out the same soft glow. The farther ones will, of course, appear fainter than the nearer ones. If you see one lamp looking much dimmer than another, you could reason that it's not inherently weaker, it's just farther away. Leavitt's Cephids are like those standard street lamps. Thanks to her work, astronomers realize that if they spot a Cepheid variable star in the sky, they can determine its true brightness by observing the rhythm of its pulsation. A Cepheid with a long, leisurely pulsation cycle is a very luminous giant, while one with a quicker beat is less luminous. By comparing a Cepheid's true brightness, as inferred from its period, to how dim it looks from Earth, the distance to that star can be calculated. Leavitt's period luminosity law, as it came to be known, meant that for the first time the universe had reliable standard candles. These stars could tell us the distances to clusters and galaxies far beyond our Milky Way. In the 1920s, not long after Henrietta Leavitt's discovery, astronomer Edwin Hubble was scanning the sky through the Mount Wilson Observatory's 100-inch telescope, at that time the largest in the world. He was studying what were then called spiral nebulae, mysterious spiral-shaped clouds of light. One of these was the Great Andromeda Nebula. Many scientists believe these spiral nebulae were just nearby clouds of gas or star clusters within our Milky Way. The universe, they thought, essentially ended at the borders of our galaxy. But late one night in 1923, Hubble found a faint blinking star in the Andromeda Nebula. It was a Cepheid variable, a fortunate find, as if a lamppost of known wattage had suddenly appeared on a distant shore. Using Leavitt's formula, Hubble calculated how far away this star must be. The number was staggering, well over 1 million light-years, later refined to over 2 million. This was far outside the confines of our Milky Way. In that moment, Andromeda was revealed to be not a small nearby cloud, but an entirely separate galaxy. an island universe as vast as our own. Hubble's discovery, made possible by Leavitt's celestial yardstick, expanded our understanding of the cosmos immensely. The universe suddenly grew from a single galaxy to countless galaxies scattered across unimaginable distances. Think of the enormity of that revelation. What had seemed to be little smudges of light on old photographs were proven to be other galaxies, each containing billions of stars. Humanity's conception of existence ballooned outward in one of the greatest leaps of knowledge ever achieved. And at its heart was the quiet work of Henrietta Leavitt, who never lived to see the full impact of her discovery. She passed away in 1921, not knowing that her period luminosity relation would be the very tool to measure the universe. She once wrote, humbly, "A straight line can be readily drawn among each of the two series of points corresponding to maxima and minima." In that simple comment about her graph of Cepheid stars lay the key to the cosmos. Let us pause to appreciate the scene. A gentle woman in a modest office, meticulously noting the flickers of distant stars, found a pattern that unlocked the heavens. Her work was like listening to the heartbeat of the universe and realizing it could tell time. Because of her, we can now say with confidence that the Andromeda Galaxy lies about 2.5 million light-years away, and that the universe extends far beyond, teeming with other galaxies even further out. Leavitt gave us a way to measure the unmeasurable, to extend a ruler across deep space. This chapter reminds us that our understanding of stars isn't just born from the stars themselves, but also from human curiosity and ingenuity. It's a comforting thought. As small as we are, sitting here on our little planet through patience and intellect, we have found ways to touch the stars and gauge the breadth of the cosmos. Each quiet worker at a desk, each careful observation, each scratch of pen on paper can ripple outward to cosmic importance. As we continue our journey, carrying with us the tools and knowledge these pioneers bestowed, we return our focus to the stars themselves. We've learned how to classify them and measure their distances. Now, soothed by the dedication of those who helped us understand, we venture back to the stars' own lives, to the places where they are born. Our next stop is a realm of cosmic clouds and tranquil darkness, where new stars open their eyes for the very first time. Stars, like all of us, have a birthplace. To find it, we must leave the familiar realm of starry skies and journey into immense nebulae, vast, gentle clouds of gas and dust that drift through space. These nebulae are the cradles where new stars are born, and entering one is like entering a softly glowing cathedral in the cosmos. Imagine flying slowly into a great cloud in the Milky Way. At first it's dark and cold. Starlight from outside is faint and patchy, obscured by swirling dust. But as we glide deeper, we begin to see a dim luminosity around us, like the first light of dawn illuminating mist. This is the stellar nursery, the womb of stars. Not all nebulae look the same, and their appearances tell different stories of how they shine. Some nebulae glow with their own light. These are called emission nebulae. Here, young, hot stars born within the cloud flood their surroundings with energetic ultraviolet light. The gas in the cloud responds by glowing at specific colours, much like a neon sign glows when electrified. In these nebulae, hydrogen, the most abundant element, often emits a ruby-red light when ionized, painting the nebula with a rosy hue. Other elements contribute too. Oxygen can glow in green or blue, and sulfur in deep red. The famous Orion Nebula, a stellar nursery visible just below Orion's belt, is one such emission nebula. Its cloud is energized by a cluster of newborn stars at its core, and as a result the nebula shines in a palette of soft colors. If you've seen photographs of Orion or other nebulae taken by telescopes, you might recall ethereal pinks, greens and blues swirled together like cosmic watercolor. These colors are often a translation of elements and energies that our eyes alone can't see. For example, in some images of nebulae, scientists assign visible colors to invisible wavelengths. Blue might represent glowing oxygen gas, red might indicate sulfur, and green can show hydrogen mixed with nitrogen. The result is a breathtaking visual story, a silent fireworks display revealing where different gases reside and how the young stars are shaping their birthplace. In reality, if you were floating there, the light would be too faint for your eyes to see such vibrant colours. You'd perceive only a ghostly grey or red haze, but through long exposures and specialised filters, our telescopes bring out the hidden hues, allowing us to witness the delicate artistry of star birth. Other nebulae do not glow on their own, but instead reflect the light of nearby stars. These are the reflection nebulae, and their beauty is more subtle and cool. Imagine a street lamp on a foggy night. The lamp itself might be hidden, but the mist around it glows a gentle blue from the scattered light. In the cosmos, dust grains in a reflection nebula scatter the light from a bright star or stars embedded within. And because blue light scatters more easily, the nebula takes on a soft blue sheen. A lovely example is the nebulosity around the Pleiades star cluster. When you gaze up at the Pleiades on a clear autumn night, you see 6 or 7 bright stars. If your eyes were more sensitive, you'd also perceive a faint haze around those stars. That is a reflection nebula, starlight ricocheting off ancient dust left over from the cluster's formation, or perhaps from a cloud the cluster is passing through. It's a bit like seeing the dust motes in a sunbeam, illuminated but not emitting light themselves. Reflection nebulae have a calming, thought-provoking beauty, as if they prefer to whisper the star's presence rather than shout it. Then there are dark nebulae, which might be the most enigmatic of all. These are dense clouds of gas and dust that don't glow or reflect light, at least not in visible wavelengths. Instead, they appear as silhouettes, blocking the light of stars or bright nebulae behind them. To the eye, they look like holes in the starry sky, patches where the stars seem to be missing, cut out by an invisible hand. One of the most famous is the Horsehead Nebula in Orion, a small dark nebula shaped remarkably like a horse's head, silhouetted against a curtain of pink emission light. When you see a photograph of it, you sense depth and texture, the inky black cloud in the foreground and the gentle rose-coloured glow of ionized hydrogen behind. Such dark nebulae are not empty at all. They are full of the raw material for future stars. In their lightless interiors, protected from harsh starlight, molecules and dust grains can coalesce. They are like cosmic cocoons, places where, hidden from view, the seeds of new suns are taking shape. Let's take a gentle flight through one particular stellar nursery to bring all these pieces together. We find ourselves approaching the Great Orion Nebula, about 1,500 light-years from Earth. As we drift in, the scene around us is one of serene grandeur. Starlight from a cluster of hot young stars at the nebula's heart, the trapezium, bathes the cloud in a soft radiance. The inner region of the nebula is all aglow, an emission nebula, a cavernous space where the gas has been hollowed out by intense ultraviolet radiation and winds from those infant stars. The gas on the cavity walls glows a pinkish red from ionized hydrogen. Deeper in, close to the energetic stars, we catch a subtle greenish cyan tint. This is oxygen shining where the gas is hotter. We also notice delicate veils of darkness, tendrils and pockets of dust that haven't yet been eroded away. Some are reflection nebulae at their edges, shining blue where they face the starlight, and some parts are true dark nebulae, impenetrable and waiting. As we float further, we come upon a breathtaking sight. The pillars of creation inside the Eagle Nebula, another stellar nursery a bit farther away. They rise out of a glowing cloud like 3 towering mountains of shadow against light, columnar giants of dust and gas many light-years tall. Their tips are being sculpted by the glare of nearby massive stars. Each pillar's surface shimmers faintly. That's the outer layer of gas being ionized and evaporated by starlight, while the interior remains cool and dark. Within these pillars, in tiny hidden pockets that even our eyes cannot see, new stars are coalescing. It is a scene of utmost patience and tranquility. Over several 100,000 years, a dense knot within a pillar will gather more and more material under gravity's tender pull, growing hotter and denser, until one day, perhaps with a gentle flicker, a new star's light will dawn where there was darkness. The wispy columns hide these newborn stars within their folds, like a nursery curtain around a sleeping baby. In fact, throughout the Orion Nebula and other stellar nurseries, this slow, patient work of gravity is proceeding quietly. Portions of the cloud that are a bit denser than their surroundings begin to shrink under their own weight. As they contract, they fragment into smaller clumps, each clump destined to become a star, or sometimes a system of multiple stars. The dust within helps radiate away heat, allowing the collapse to continue calmly. Over tens of thousands of years, a clump's core grows denser and starts to warm up, like the kindling of a hidden flame. Eventually a protostar forms at the centre of the collapsing globule, a newborn star that has not yet ignited the nuclear fusion in its heart, but is alive with the heat of its formation. Swaddled in layers of dust, the protostar is still invisible to our eyes. Were we to search for it, we might only see a dark globule or a faint infrared glow betraying its presence. All around, the nebula's story is one of balance between creation and destruction, pressure and gravity. The same bright young stars that cause the nebula to shine also send out fierce winds and light that can erode the cloud, potentially blowing away material that could have formed more stars. Yet their influence also causes new stars to be born by compressing gas in some places. It's a beautiful cosmic dance, starlight sculpting the clouds into fantastical shapes, pillars, filaments, and shells. While deep inside those very shapes, new stars quietly kindle. From our serene vantage point within the Orion Nebula, we take in this scene of quiet creation. Baby stars are everywhere here, some just peeking out from their dust cocoons, others clustering in their energetic youth. The light around us is soft and diffuse, illuminating swirls of gas in pastel colours. If you listen with your imagination, you might even sense a gentle cosmic lullaby, the collective murmur of countless atoms and dust grains slowly coming together, the distant radiance of newly lit stars shining through gauzy veils. This is the nursery of the cosmos, peaceful, patient, and yet full of anticipation for the brilliant lives to come. Before long, one of those contracting clumps will reach a critical point. The protostar at its core will become hot and pressurized enough that hydrogen atoms begin to fuse into helium, releasing a burst of energy. In that moment, a star is truly born, and it will emerge from its dusty womb to take its place among the stars in the sky. But that moment, the first light of a new star, belongs to the next chapter of our journey. For now, we linger a bit longer in the calm of the nebula, enveloped in its soft glow and gentle darkness, witnessing the earliest chapter in the life of a star. Deep inside a collapsing cloud core, a new star is coming into the world. In the last chapter, we left our forming protostar just on the verge of igniting its nuclear fire. Now we gently zoom in on this embryonic star, still swaddled in its dusty cocoon. The scene is one of both calm and activity. Calm because everything is muffled by layers of dust and gas. Activity because complex things are happening behind that veil. At the centre of a dense globule, the temperature and pressure have been building. The protostar is like a warming ember, growing ever hotter as gravity squeezes it. Before a star truly turns on, it spends a brief early phase as what astronomers call a T-Tauri star. These are essentially stellar toddlers, young, feisty, and a bit unruly. T-Tauri stars are known for their variability. Their light can flicker and change as they convulse with magnetic activity, and for the strong stellar winds they blow out. Our newborn star is in this spirited stage. It hasn't yet settled into the steady glow of adulthood, so it may brighten one week and dim the next, like a little flame flickering in a breeze. It also sends out gusts of charged particles, a stellar wind far stronger than the present-day wind of our middle-aged sun. Yet, despite these energetic outbursts, this baby star is still gentle in our view. Its light is mostly hidden, emerging only as a faint warm glow diffusing through the opaque cocoon around it. If we could peek at it directly, perhaps with infrared vision, we might see patches of the forming star's surface cooler or hotter, and loops of gas arcing out from it, much like gigantic versions of the flares and prominences we later see on mature stars. Surrounding the protostar, like a skirt around a dancer, is a protoplanetary disk, the birthplace of planets. As the cloud collapsed, some of the material began orbiting the centre, flattening into a spinning disk of gas and dust. Think of a pizza dough being spun into a flat circle, or a potter's wheel shaping clay. In this disk, countless dust grains are gently colliding and sticking together. Over years and decades, mere moments in cosmic time, they form tiny aggregates. Over thousands of years, those become pebbles and rocks. The disk is rich and thick, glowing faintly with the heat of formation and the light of the growing star. Eventually, this disk will give rise to planets, moons, asteroids and comets, an entire solar system in miniature, but for now it is still a chaotic mix of dust and gas. The young star is actively feeding from this disk. Gas from the inner disk is spiraling down onto the star, adding to its mass. Imagine a gentle rain of material falling onto the star's surface from the disk above, a process that fattens the star up. In response, the star periodically burps out some of that material. Indeed, the protostar is devouring its disk with a jabber-like appetite, as one astronomer vividly put it. The excess energy and material find escape along the star's poles, the path of least resistance where the newborn's growing magnetic field funnels them. The result is one of the loveliest sights in star formation, twin jets of hot gas shooting out into space from the north and south poles of the star. It is as if the star is breathing out for the first time, announcing its arrival. These jets blast into the surrounding nebula at hundreds of kilometers per second, creating glowing shock waves where they ram into the colder cloud material. In photographs, they appear as thin, pencil-straight beams emanating from a hidden source, sometimes stretching light years long. Astronomers have a term for the luminous knots and patches that appear where these jets plough into the cloud. Herbig-Haro objects, essentially cosmic splash effects. But we might simply think of them as the star's birth announcement, marking its presence with a subtle fireworks show. The jets themselves are narrow and partly ionized, like twin laser beams lancing through the darkness. As they collide with the nebular gas, they carve out clearings and stir up the interstellar medium, a bit like a stream of water carving grooves as it hits a pile of sand. Through this action, the newborn star is literally shaping its environment, blowing away the remnants of the cocoon from which it emerged. Inside the cocoon, meanwhile, the star continues to contract and heat. Finally, in the deepest core of the protostar, fusion ignites. It might happen quietly, over a span of days or weeks, as the temperature surpasses about 10 million degrees and hydrogen atoms begin to combine into helium. The star's first true stellar light is born from this fusion fire. At this moment, the star graduates from its tumultuous infancy. It has entered the main sequence phase of life, where it will spend millions or billions of years in a stable glow. The wild variability of youth calms down, the stellar winds slow a bit, and the jets gradually fade away as the disk is either accreted or blown out. Now our star has become a steady beacon. It has shed much of its birth cloud, emerging like a butterfly from its chrysalis of dust. The once hidden infant can now shine forth into the galaxy, announcing in a gentler but more enduring way that it has joined the cosmic community of stars. Imagine the scene from afar. A new star, perhaps, with a subtle, newborn blueness or whiteness to its light, illuminating the dispersing remnants of the nebula that once hid it. Around it, a thin, silvery disk remains, the last traces of the material that didn't fall into the star. In that disk, future planets are quietly coalescing, but the star itself is now stable and quietly humming with the constant energy of fusion. In the grand timeline of the cosmos, this transition from protostar to full star is like the first breath of a baby, a delicate, miraculous moment that happens in silence, witnessed only by the surrounding dust and gas. We have journeyed through darkness to witness that first gentle glow. Our once turbulent T-Tauri has settled into a calm, radiant young star. With its arrival on the main sequence, the star's long, quiet adulthood begins, a topic we will explore in the next chapter. For now, let us bask in the soft and steady light of this new star, knowing that deep in its core, tiny atoms are fusing and releasing the energy that will light up its corner of the galaxy for ages to come. Our star has now entered the most peaceful chapter of its existence. Having shed the turbulence of youth, it settles into a long, steady burn on the main sequence, the stellar equivalent of adulthood. Day after day, century after century, the star shines with a comforting constancy. If we could sit nearby, at a safe distance, and watch, we would see a very reassuring sight. A round, glowing orb of light, stable in size and brightness. Inside, deep in the core, a miraculous balance is at play. The force of gravity still tries to pull the star's mass inward, but it is perfectly countered by the pressure of energy radiating outward from the nuclear fusion in the core. This state is called hydrostatic equilibrium, though we might simply think of it as the star's inner peace, a harmonious balance between gravity's inward embrace and the outward gentle push of light and heat. Because of this equilibrium, the star neither collapses nor bloats uncontrollably. It holds itself together in a beautiful, enduring poise. At the heart of the star, hydrogen fusion is quietly taking place, turning the star's core into a cosmic kitchen. In stars like our Sun, the dominant recipe is the proton-proton chain. 4 hydrogen nuclei, protons, are ultimately combined into one helium nucleus in a series of carefully choreographed steps. It's a bit like a slow, 3-step dance, where protons join to form deuterium, a proton-neutron pair, then gather another proton to become helium-3, and finally 2 helium-3 nuclei merge into helium-4, releasing 2 protons back into the mix. Each of these tiny mergers releases energy, a dribble of pure light born from a minuscule amount of mass converted via Einstein's famous E equals mc squared. The proton-proton chain is a patient process, especially in a star the size of the Sun. Any given proton in the Sun's core might wait billions of years before it successfully fuses, but there are so many protons that collectively they keep the furnace burning steadily. This gentle, sustained fusion is what powers the star's shine and warmth, and will continue to do so for eons. In more massive stars, a different fusion process takes the lead, the CNO cycle, named for carbon, nitrogen and oxygen. Think of this as a more rapid cooking cycle in a larger star's core. Here, a carbon atom acts like a seasoned cooking pot, helping to fuse 4 hydrogens into 1 helium, and emerging at the end unchanged, ready to start the cycle again. Because the carbon, nitrogen and oxygen serve as catalysts, they facilitate the fusion but are not consumed by it. The CNO cycle runs faster than the proton-proton chain, but it needs a hotter core to get going. Massive stars, which have much higher core temperatures, utilize this cycle to generate their prodigious energy output. We might imagine the CNO cycle as a master chef's recipe. The ingredients, hydrogen nuclei, are cooked quickly with the help of a sturdy pot, carbon, producing the helium and a great deal of energy in a shorter time. The end result of both the proton-proton chain and the CNO cycle is the same. Hydrogen becomes helium and energy pours out, but the pace and style of the cooking differ. What's important is that in each case the star has found a way to sustain itself, converting matter to light in a deep, serene fire that can last for millions or billions of years depending on how fast it eats its fuel. All the while, the star's energy flows outward from the core to the surface and then into space. When it finally leaves the star as sunlight or starlight, it has travelled hundreds of thousands of years from the core to escape. This sunlight is the star's gentle gift to any worlds that might circle it, the warming rays that could nurture life, the illumination that can cast shadows on distant planets. Our own sun's light is the result of processes that have been ongoing for about 4.6 billion years and will continue for about as long again. Such is the tranquil longevity of a main sequence star. Yet, even in this placid middle age, stars are not entirely unchanging. Our Sun, for instance, has its own subtle cycles and moods. Every 11 years or so, it goes through a cycle of magnetic activity. At the peak of this cycle, we see a greater number of sunspots, dark, cooler patches on the sun's bright surface where intense magnetic fields poke through. These sunspots are like transient freckles or islands on the stellar ocean of light, often appearing in groups and then dissipating over weeks or months. When the sun is more active, it also produces more solar flares and coronal mass ejections, bursts of energy and plasma that leap from its surface. During quieter periods, fewer spots dot the sun's face and it settles into a more uniform shine. These changes are modest. Even at the most active times, the sun's total brightness only varies by a fraction of a percent. If you were floating near the sun, again at a safe distance, you might not notice a difference in the sunlight on your skin between the active and quiet phases. But the changes are enough to influence space weather. For instance, Earth's auroras, the northern and southern lights, tend to dance more vigorously when the sun's mood is feistier and it sends gusts of charged particles our way. Through it all, the star continues to breathe in its own way. The constant outflow of particles from its upper layers, called the stellar wind, is like a very tenuous breeze permeating the solar system. In the case of our sun, we call it the solar wind. This wind is composed of electrons, protons, and other subatomic particles streaming outward at hundreds of kilometers per second. Though incredibly thin by earthly standards, almost a vacuum, it travels far, carrying the sun's influence to the far reaches of our solar system and beyond. When a comet swings near the sun, it is the solar wind and sunlight that pushes its tail back, always pointing away from the sun. The solar wind also carves out a vast protective bubble around our solar system, called the heliosphere, shielding us from some of the harsher cosmic rays that roam interstellar space. We can think of it as the star's gentle breath, expanding outwards and softly enveloping any orbiting planets in its protective embrace. From a human perspective, a main sequence star like the sun seems almost eternal and unwavering. Generation after generation can look up at the sky and count on the same sun rising every morning, shining with the same golden glow. In truth, of course, the star is using up its fuel, atom by atom, in those deep nuclear fires. But so vast is its reservoir of hydrogen, and so efficient its energy production, that the star's brightness changes imperceptibly over millennia. It truly is a long, quiet life as far as stars go. A more massive star will live out its main sequence life faster, shining bluer and hotter, exhausting its core fuel in a few million years. A small red dwarf star, by contrast, sips its hydrogen slowly, and can shine for hundreds of billions of years with barely a flicker. Our sun is somewhere in between, a reliable yellow dwarf with a total main sequence lifespan of about 10 billion years. In this tranquil phase, the star may also host worlds around it, perhaps encircled by planets, asteroids, and comets that formed from that protoplanetary disk we described earlier. The star's steady light nurtures those worlds with warmth and energy. If life arises on any orbiting planet, it will owe its existence to the constancy and benevolence of this stage of starlight. Imagine an Earth-like planet bathed in the glow of a sun-like star. Each day the sky brightens and a nourishing light falls across landscapes and oceans, driving winds and rains and the rhythms of life. All the while the star itself quietly converts hydrogen to helium, keeping a delicate balance that allows life's fragile chemistry to flourish under its gaze. We have now journeyed with our star through the majority of its life, a journey measured in billions of years of radiant, steadfast shining. But like all chapters, this long middle act will one day draw to a close. When the hydrogen in the core becomes scarce, the star will face the first real change it has experienced since youth. In the next chapter, we will gently explore what happens when a star exhausts the fuel of its main sequence and begins to grow into a new, more expansive phase. For now, let's take a comforting breath and appreciate the stellar present, the gentle, golden afternoon of a star's life, stable and serene, casting its light across the cosmos. Stars are not always solitary wanderers. Many are born together in groups, sharing a common origin like siblings in a stellar family. To see this in action, let's gently travel to a star cluster, a place in space where dozens, hundreds, or even millions of stars gather in a family group. There are two major kinds of star clusters, each with its own character: open clusters and globular clusters. First, picture an open cluster. These are like stellar playgrounds, relatively small, loosely bound gatherings of stars that recently formed together from the same nebula. They are often found sprinkled along the spiral arms of galaxies, including our Milky Way. Imagine drifting through one. The space around you is filled with bright, youthful stars. Many of them are hot and blue, shining intensely because of their larger mass and youthful energy. They haven't had time to wander far from the cloud that birthed them, so they remain clumped in a group that might span only a few dozen light years. The Pleiades is a famous example of an open cluster, also known as the Seven Sisters. If you gaze up on a clear night, you can see this cluster as a tiny smudge of blue-white stars in the constellation Taurus. Through a telescope, it resolves into dozens of luminous stars. They're all a few 100 million years old, teenagers in stellar terms, and still surrounded by a delicate haze of reflection nebula, the last wisps of the cloud from which they formed. Open clusters feel casual and friendly. The stars within them are only loosely held by gravity, so over time, tens to hundreds of millions of years, the cluster will gradually disperse. It's as if, after growing up together, the stars eventually move out and drift away into their adult lives throughout the galaxy, like children growing up and leaving home. In the Wild Duck Cluster, another open cluster known to astronomers as M11, we see a rich swarm of stars that resembles to some eyes a flight of ducks, but given a few 100 million years, even this flock will scatter. Now in contrast, imagine a journey to a globular cluster. This is a very different sort of family, an ancient city of stars, crowded and rich with history. Globular clusters are nearly spherical swarms containing not thousands but hundreds of thousands, or even millions of stars, all tightly bound in a gravitational embrace that has lasted for billions of years. They reside mostly in the halo of our galaxy, orbiting around the Milky Way's centre like old retirees around a bustling town. As we float into the core of a globular cluster, the sky around us would be astonishing. Brilliant stars in every direction, far denser than the starry sky of Earth's night. The stars here are older, often with a golden or reddish tint. As many are red giants or steady, long-lived sun-like stars that have aged past their blue youthful hues. It's like walking through an ancient lamplit city at night, where every lamp is a star that has been shining for 10 billion years. The cluster's heart is crowded. Stars can be only a fraction of a light year apart. If there were planets in such a region, their night skies would be jewelled with hundreds of stars brighter than any we see from Earth. One famous globular cluster is Omega Centauri, which you can spot with the naked eye from the southern hemisphere as a fuzzy star. Through a telescope, it blooms into a glittering ball of over 10 million stars. Astronomers suspect Omega Centauri might even be the remnant core of a small galaxy, long ago swallowed by the Milky Way, a testament to how massive some globular clusters can be. Globular clusters are old, among the oldest formations in the galaxy. The stars within them are typically population 2 stars, those grandparent stars we mentioned earlier, meaning they formed in the early epochs of our galaxy and thus contain very few heavy elements. In these dense clusters, time seems to stand still. Stars evolve, yes, but the cluster as a whole retains its identity over eons. We can almost sense the ancient hush as we observe one. Imagine the collective light of a million elder stars bathing you in a gentle amber glow, their combined gravity forming a cradle that keeps the family tightly knit through galactic travels. Even star clusters have their own way of keeping time, and astronomers have learned to read their clocks. When a cluster forms, it contains stars of all masses born together, high mass, mid-mass, and low-mass stars in one cohort. The most massive luminous blue stars live very short lives, so they perish first, in supernova explosions or by evolving into giants and then fading. As a cluster ages, progressively less massive stars exhaust their hydrogen and leave the main sequence. On a graph, the Hertzsprung-Russell diagram of the cluster's stars, the bright blue stars peel off the main sequence line first, then white stars, then yellow. The point on this diagram where the cluster's stars are currently turning off the main sequence, known as the main sequence turn-off point, serves as a stellar age indicator. In a young open cluster, the turn-off might still be at very bright blue stars, indicating the cluster is only tens of millions of years old, since even the big stars haven't all died out yet. In an old globular cluster, the turn-off is down at much dimmer redder stars. All the hot massive stars are long gone, meaning the cluster is likely on the order of 10 billion years old. It's as though you looked at a family photo and noticed that all the eldest siblings are missing from the picture. You infer they've grown up and moved on, or in the stellar case passed on, and only the younger siblings remain, telling you how much time has passed. By measuring the colour and brightness of the stars at this turn-off point, astronomers can estimate the cluster's age with remarkable precision. In this way, these stellar families help us gauge the timeline of our galaxy itself. As we drift back from our close look at clusters, we appreciate that stars are not just points of light scattered randomly. Many carry with them the subtle companionships of their birth environments. Even our Sun is thought to have been born in an open cluster long ago, alongside sibling stars that have since dispersed throughout the Milky Way. Some of those siblings may still be out there, detectable by their chemistry and motion, a kind of stellar DNA test indicating shared parentage with our Sun. In the cosmic scheme, clusters are families that eventually part ways. Yet, for the duration of their togetherness, they are one of the most beautiful sights nature offers, communities of light shining together in the dark. Whether in the tight elder symphony of a globular cluster or the youthful lilting chorus of an open cluster, we find that stars, like people, often live in communities that shape their early lives. Eventually the members may go their separate ways, but they carry traces of that shared origin in their motions and compositions. Having seen how stars live alone and together, we now turn to the way we humans have connected with the stars through story and myth, finding patterns and meaning in their arrangements across our sky. Since ancient times, human beings have looked up at the stars and felt a profound connection, a mixture of wonder, curiosity, and comfort. In the silent pinpoints of light, our ancestors saw patterns and spun stories, finding in the random scatter of stars a rich tapestry of meaning. The night sky became a grand storybook, with each constellation a chapter, each star a character. In this way, the cold, distant cosmos was woven warmly into the fabric of human culture. On this part of our journey, we drift not through a nebula or cluster, but through the world's collective imagination, exploring a few of the gentle tales and guides that the stars have offered us. High in the northern sky, a great bear prowls among the stars. The ancient Greeks saw her as Callisto, a maiden transformed into a bear and placed in the heavens by Zeus. We know her today as Ursa Major, the Great Bear, her hindquarters marked by the bright stars of the Big Dipper. In the Greek myth, Callisto's son, Arcas, nearly hunts his enchanted mother until Zeus intervenes and turns him into a smaller bear, Ursa Minor, placing him nearby in the sky. As a final touch, Zeus stretches their tails, or perhaps ties them to a celestial pole, explaining why bears in the sky have such long tails, unlike earthly bears. Every night, Ursa Major circles the North Star, never setting, as if on eternal watch. To many people around the world, these stars suggested a bear. Ancient peoples of Siberia, North America, and Europe independently imagined a large bear figure there, often with hunters following it. It seems something about that pattern, a body and a crooked tail, speaks to our storytelling minds. We can picture ourselves around a campfire, pointing upward as someone traces the shape of the bear with an outstretched hand, bringing the constellation to life against the dark. Not far from Ursa Major, in the shoulder of the Taurus constellation, a tiny cluster of stars has inspired myths in cultures everywhere, the Pleiades or Seven Sisters. Look up on a clear night in late autumn or winter, and you'll see a tight, misty knot of 6 or 7 pinpoints. To Greek eyes, these were the 7 daughters of Atlas and Pleione. Their beauty attracted the hunter Orion, who pursued them relentlessly. To save them, Zeus placed the sisters in the sky. But even there, Orion continues to chase them across the heavens each night, as the 2 constellations rise and set. If you have ever counted the Pleiades, you might notice only 6 stars are easily visible to most eyes. The Greeks noticed this too and wove it into their story. One sister, variously named Merope, or Electra in different tellings, is missing or dim, perhaps because she fell in love with a mortal and hides her face in shame, or in another version because she left her post to grieve the fall of Troy. This motif of the lost Pleiad, a missing 7th star, appears in other cultures as well. The Maori of New Zealand, for instance, tell of a younger sister who ventured away. It's a gentle reminder of how people separated by oceans and centuries still looked at the same stars and found similar patterns, filling in the gaps with story. Far to the south, visible from equatorial and southern lands, the grand constellation of Orion straddles the celestial equator. Many know Orion as a Greek hunter, the figure with a belt of 3 stars and a sword hanging from it. But Orion, perhaps due to his striking pattern, has inspired tales in many cultures. In the deserts of southern Africa, for example, the Yuhwansi, a San people, see a very different scene. 3 zebras, the 3 stars of Orion's belt, are being pursued by a hunter. In their telling, the bright star we know as Rigel is not a foot of Orion but a separate figure, a hunter who has shot an arrow, the line of stars in Orion's sword, at the 3 zebras of Orion's belt. He missed his mark, the arrow has passed through and now stands beyond them. The red star Betelgeuse, marking Orion's shoulder in Western charts, is seen as a lion watching the hunter and the zebras from a distance. This vivid tableau, different from the Orion of Greek mythology, nevertheless uses the same stars to tell a story of hunter and prey, reflecting the environment and values of the people who imagined it. Meanwhile, in other parts of Africa, Orion's belt and sword have been seen as 3 hunters chasing 3 pigs, in the lore of the Swana people, or as a ladder used by celestial beings. The skies are a mirror to diverse cultures, each sees its own experiences reflected there. While some constellations provided canvases for myths and legends, the stars collectively have also served practical and spiritual needs. Few examples are as inspiring as the wayfinding traditions of the Polynesian navigators. Imagine being in a double-hulled canoe in the middle of the Pacific Ocean thousands of years ago. No land in sight, no compass, only the dome of sky and sea. By day one might read wave patterns or the sun's path, but by night the stars become a map. Polynesian sailors knew the rising and setting points of hundreds of stars, using them like a grid to chart their course across vast distances. Each star has a specific bearing. For instance, they knew that when a particular bright star, say Herculea, the star of gladness, known elsewhere as Arcturus, rose or set at the horizon, it indicated the direction of a certain island or the latitude of their canoe. The navigators memorized star lines, sequences of stars that would ascend and descend along the horizon as the night progressed, effectively having multiple signposts through the night. They also read subtle cues. The colour and height of stars could hint at weather. The presence of certain stars at dusk or dawn signalled the seasons for voyages. In a very real sense, the Polynesians made the stars their partners in exploration. There's a beautiful image one can hold, a navigator lying on his back in a gently rocking canoe, looking up at the pure dark sky strewn with stars, and knowing that his beloved home island lies in the direction of a certain star cluster setting in the west, or that by dawn a particular star will lead him to land. To them, the sky was not an abstract map, but a familiar family of guides, each star with a name and a role in the story of the ocean. These techniques enabled voyages from Tahiti to Hawaii and beyond, well before modern instruments, guided only by starlight, ocean swells, and the wisdom passed down through generations. The Milky Way itself, that band of diffuse light arching across the sky, has inspired perhaps the greatest variety of interpretations. To the Greeks and Romans it was a spilt drink of milk, hence galaxy from galactos, milk. But turn to the cultures of Australia, and the Milky Way becomes not a river of light, but the dark shapes within it form the figures. The Aboriginal peoples have rich traditions tied to the dark dust lanes of the Milky Way. One famous example is the emu in the sky, known to several Aboriginal groups. Instead of connecting stars, this constellation is outlined by the great dark rifts of the Milky Way. The absence of starlight forms the long neck, body and legs of a running emu. On a clear autumn evening in Australia, the emu stretches from the Southern Cross, which marks its head, across the sky. What's more, the emu in the sky is not just a visual story, but a seasonal calendar. In the traditions of the Wiradjuri and other groups, when the emu's dark form appears in a certain orientation at dusk, for example, when it's just rising from the horizon after sunset, it coincides with the time when emus on Earth are nesting, and thus it's forbidden to gather their eggs. Later in the year, when the emu is seen fully overhead at dusk, it signals that the eggs have hatched, and it is time to go collect emu eggs and chicks. Such knowledge is a blend of astronomy and ecology, woven into story, an elegant synergy of sky and earth. In the Andes, the Inca also looked at the Milky Way's dark patches rather than its stars and saw a very different set of creatures. They identified dark constellations, Yanafuyu in Quechua, shapes of animals and objects outlined by the black nebulae against the glowing star field. In the Milky Way's bulge near Scorpio, they saw a great serpent, Machacuay, slithering along the sky. A nearby dark blotch was a toad, Hanpatu, crouching in the cosmic river. Most prominent of all, stretching by the Southern Cross, they saw Yakana, the mother llama, followed closely by a smaller llama, perhaps her calf or a llama being led. The two bright stars of Centaurus, Alpha and Beta Centauri, were seen as the llama's shining eyes. The Inca related these celestial forms to the seasonal rains and livestock fertility. For example, when the llama's eyes, those two bright stars, appeared at dusk at a certain time of year, it was an omen related to the well-being of actual llamas. The sky was thus a living map of their world, connecting the agricultural and pastoral cycle with the motions above. Each of these stories, Greek, Aboriginal, African, Polynesian, Incan, and so many more we haven't touched, highlights a facet of how humans connect to the cosmos. Lying beneath different skies, speaking different languages, our ancestors all looked upward and felt the need to translate the stars into something human. The scientific truth of stars, that they are distant suns, nuclear furnaces, balls of plasma, is awe-inspiring in its own right. But alongside that truth lives another truth, that the stars are also our storytellers, our calendar, our compass, our inspiration. They anchor us in time and place. They remind us of heroes, monsters, animals, lovers, and quests. They guide voyagers across open oceans and nomads across trackless deserts. They mark seasons of planting and harvest, of hunting and ceremony. And perhaps most beautifully, the stars bridge generations. The same Pleiades that we see tonight were seen by a farmer in ancient Greece, by a navigator in Polynesia, by a storyteller in the Kalahari, by an Inca priest on a mountaintop, all with their own layers of meaning. When we gaze up and identify Orion or the emu or the llama, we participate in a human tradition as old as language. Now, having journeyed through the human stories of the stars, we return our focus to the star we've been following through its life cycle. It has lived a long, stable life, shining on any who might look up from nearby worlds. But even a quiet life under the stars must eventually yield to time. In our next chapter, we will watch our star enter its twilight years, expanding and changing in ways that will transform it into something truly majestic, a red giant and beyond. Before we move on, take one last look at the sky in your mind's eye. See the constellations of your own memory or heritage, and feel how the starry night, though scientifically distant, has always been close to the human heart. Even the longest and most unchanging day must eventually find its evening, so it is with our star. After billions of years of steady happiness on the main sequence, quietly turning hydrogen into helium at its core, the star begins to sense a profound change. The hydrogen fuel in the core is nearly spent. Without that fusion fire, the core can no longer hold up against gravity as effectively. The core starts to contract, pulling inward under its own weight, and as it does, it heats up. Much like a bicycle pump gets warm when you compress the air inside. In the surrounding shell, just outside the core, hydrogen that wasn't previously hot enough now ignites in a fury of fusion. This shell burning injects new energy into the star's outer layers, causing them to expand outward. What does this transformation look like? The star's surface swells to enormous proportions, tens, even hundreds of times its previous radius. Imagine our sun swelling until it engulfs Mercury and Venus, perhaps even reaching toward Earth's orbit. As it expands, its heat is spread over a much larger area, so the surface cools from white-hot to a gentler orange-red hue. Our star, once a yellow-white beacon, has become a red giant. Its light now has a richer, more ruddy cast, a sunset colour, as if the star itself is entering its twilight. And indeed, this is a star's old age, a time of great change but also of a kind of majestic splendour. From afar, our once modest star now dominates its region of space, a bloated luminous ruby in the sky. Inside the red giant, the core continues to shrink and heat, under gravity's relentless pressure. New physics comes into play. The core's matter is squeezed into a dense state called electron-degenerate matter, where atoms are so tightly packed the electrons create a pressure of their own. The temperature races upward to a critical point. Then, in a flash, a new fire ignites. When the core temperature hits roughly 100 million degrees, the helium that accumulated there suddenly begins to fuse into carbon. In a low-mass star like our Sun, this onset of helium fusion happens almost instantaneously, in what astronomers call the helium flash. It's as if, deep inside the star, a whole cluster of fusion candles are lit all at once. This could be a catastrophic explosion, but in the dense core the energy is absorbed almost as quickly as it's produced, so it propagates outward more like a silent firework than a shattering blast. The star's core, now powered by helium fusion, expands a bit and actually calms the star's outer layers, causing the star to contract slightly and become hotter in colour again for a time. One could say the star gets a second wind. Having burned helium in its core to carbon, the star finds a new, but much shorter-lived stability. This phase is sometimes called the helium-burning phase, and for a while, perhaps tens of millions of years, the star shines a bit bluer and smaller than its maximum giant size. However, helium too is a finite fuel. When the core's helium is exhausted, our star faces its final acts. What remains in the core is carbon and some oxygen, ash of the helium fusion, so to speak. The core again begins to contract, and around it a shell of helium now ignites, adding to a still active hydrogen-burning shell outside of that. The star swells up once more, even larger this time, into what's known as the asymptotic giant branch phase, essentially a second red giant stage, even more luminous but also more unstable. The phrase asymptotic isn't very poetic, but we can think of this as the star's very elder years when it becomes variable and pulsating. The star has grown so large and its gravity at the bloated surface is so weak that the outer layers begin to drift away, gently, into space. The star starts to lose mass at a significant rate via a stronger stellar wind and thermal pulses that push its atmosphere outward. We might imagine the star as a great aging monarch, gently casting off its robes. With each pulsation, a bit of the star's envelope is lifted and wafted into the surrounding space as a veil of gas and dust. During this time, if we were observing the star from a safe distance, we would see it as a long-period variable star, its brightness rising and falling over months or years as it slowly pulsates. One famous example of such a star is Mira in the constellation Cetus, a red giant that visibly brightens and dims in a cycle, roughly every 332 days. Our star, too, in this late phase would likely have a rhythmic heartbeat of light, growing a bit brighter as it contracts slightly, then dimmer as it expands again, like a slow cosmic breathing. Each pulse ejects more of the star's outer material. What was once a steady, comforting glow in the firmament has become a deep, rich but fluctuating beacon. A star in transition, painting the surrounding space with the first traces of what will become a beautiful envelope of gas. If the star had planets around it, this would be a dramatic time. By now, any inner planets, like Mercury, Venus, perhaps Earth in our Sun's case, have been scorched or even engulfed by the star's swollen radius. More distant planets would find their skies dominated by a huge red sun looming overhead. But perhaps, on the surviving far-flung worlds or moons, a keen observer might marvel at the sight of the star's outer layers beginning to form a glowing nebula, a faint, large halo starting to surround the star, tinted by the star's now reddish light. This halo is the very beginning of the next stage of our star's life story. For the red giant, these final pulsating centuries or millennia are both gentle and grand. Gentle, because the star is literally dispersing, not with a bang, but with a slow exhalation of its essence into space. Grand, because the star's appearance is imposing and regal, a far cry from the small white pinpoint it once was. In a way, the star is experiencing a kind of second childhood. It becomes larger and cooler. Some red giants have surface temperatures only a third of what they had in youth, and it's surrounded by a circumstellar cocoon of its own making, the gas and dust it's shedding. But within that cocoon, at the core, the star's central engine is nearly out of fuel. No longer can it fuse carbon. The temperatures needed for that are far beyond this star's reach. The inert carbon-oxygen core grows as helium and hydrogen around it fuse in shells, but soon even those shells will sputter out. Chapter 8 comes to a close with a poignant image. A colossal red star breathing unevenly, its once tight grip on its outer layers loosening, and a tenuous cloud forming around it. The golden years of the star are ending, but in doing so, they are setting the stage for one of the most beautiful sights in the universe. In the next chapter, we will witness the culmination of this slow shedding, the creation of a planetary nebula, a cosmic butterfly emerging from the dispersing cocoon of the red giant. For now, we drift beside our star in its red giant glory, appreciative of the paradox it presents. A dying star, yet in its death throes, it is peaceful and awe-inspiring, illuminating the darkness with a deep ruby light and the promise of new beauty to come. At last, our aging star can no longer hold on to its outer layers. With the core fuel spent and fusion dwindling, the gentle stellar breeze turns into a very slow windstorm, pushing away the star's outer atmosphere. What was once a red giant of immense size now begins to unravel, casting off its outer material into the surrounding space. The star's core, now a small, intensely hot ball of carbon and oxygen, is revealed at the centre. Its brilliant ultraviolet radiation floods the expanding cloud of expelled gas, causing it to fluoresce in beautiful colours. The star has now become a planetary nebula, not a planet at all, but a glowing shell of gas expanding away, illuminated by the remains of the star at its centre. It got this misleading name because, through early telescopes, such nebulae appeared as small, round, planet-like disks. Picture the scene, where once a red giant bloomed, now a dimmer but hauntingly lovely apparition takes its place. A ghostly nebula surrounds a pinpoint of intense light. If we were to float nearby, we'd see a spherical or perhaps bilobed glowing cloud, expanding outward like a delicate smoke ring or an ethereal bubble. The colours in this nebula are not random. They are the fingerprint of the elements being shed. Hydrogen, the most abundant element, often glows with a soft red or pink hue, sometimes enhanced by similarly red light from nitrogen in the nebula's outskirts. Closer in, we might see a teal or greenish-blue sheen, the hallmark of oxygen ions fluorescing under the central star's harsh ultraviolet light. There may be touches of other colours too, a bit of blue from helium, or white from regions where many elements overlap in their emission. Altogether, it's as if the star has released a final rainbow, a visible remembrance of the star's long life and the materials it forged and fused. This is the star's final gift to the cosmos, it returns its substance, now enriched with elements like carbon and nitrogen created in its formerly fiery heart, back to the great galactic garden where future stars and planets may use them. Planetary nebulae come in an astonishing variety of shapes. In the simplest cases, the shell of gas is mostly spherical, like an expanding soap bubble. This can happen if the star shed its mass fairly evenly in all directions. The ring nebula in Lyra, for instance, looks like a uniform smoke ring. In reality, it's a roughly spherical shell, appearing as a ring because we see the thicker edge of the sphere more clearly than the middle. But many nebulae are more complex, often bipolar or hourglass-shaped. Our star might produce two large lobes of gas instead of a single sphere, perhaps due to its rotation or the presence of an unseen companion star influencing the outflow. The result can be breathtakingly symmetric and intricate. The butterfly nebula NGC 6302 is a famous example. It truly looks like a celestial butterfly with twin wings of gas fanning out from a central body. How did such beauty arise? We believe that if the star's ejector flows out preferentially along certain axes, imagine the star had a disk or torus of material that squeezes the outflow at the equator, two opposite polar jets can carry most of the gas out, creating lobes. Many planetary nebulae show this kind of bipolar structure, sometimes with delicate filaments and tendrils tracing the edges of the lobes where the gas is colliding with earlier outflows. Other nebulae are multi-shell, perhaps the result of pulsations releasing material in phases, each shell glowing like nested halos. Some of the structures are so intricate that they almost defy imagination. The Ant Nebula, Menzel 3, reveals a set of 4 subtle rays emanating from a central region, appearing like the legs of an insect, with a bright core hidden by dust. The Helix Nebula, NGC 7293, mentioned before, looks like a giant eye in the sky, with a turquoise pupil, oxygen emission, and a red outer cornea, hydrogen emission, staring back at us across light years, hence its nickname, the Eye of God. In truth, the Helix Nebula is a cylindrical shell, and we are looking down its barrel. If we were positioned differently in space, it might not resemble an eye at all. As our star's planetary nebula expands and ages, it will likely develop a more and more diffuse appearance. Over tens of thousands of years, the nebula may grow several light years across. All the while, its internal patterns, rings, arcs, filaments, drift outward and fade like a dispersing smoke plume. During this period, the central star, once our proud red giant, has transformed into a white dwarf, a hot, small stellar core no larger than Earth, shining initially with intense ultraviolet light. It is this light that is exciting the nebula. But as the nebula spreads thin and the core cools and dims, white dwarfs, having no new source of energy, gradually fade over billions of years. The luminous colours will begin to vanish. The planetary nebula era is relatively brief, a fleeting cosmic blink of perhaps 20,000 to 50,000 years, a mere eye blink compared to the billions of years the star spent on the main sequence. For now, though, our star's legacy hangs in space as a gorgeous mist, a cosmic mandala of its life's material. If we find ourselves on a distant world in the future, looking up at the remains of this nebula, we might see something akin to a faintly glowing cloud in the night sky, perhaps visible through a telescope as a tiny disk. Intelligent beings, perhaps far in the future or from another civilization, may catalogue it as a planetary nebula and even give it a name. They may not know that this gentle apparition was once a star much like our sun that shone steadily for ages before blossoming into this final display. But we know the story. We know that we are witnessing the soft farewell of a star, a final exhalation that spreads the elements that once made up a sun, and perhaps its planets and life, back into the cosmic ecosystem. And so, the star's long journey of active life, from protostar to main sequence to giant to nebula, comes to an end. What remains at the centre is a glowing ember of a star, and around it a fading memory in the shape of a nebula. Yet, this is not truly an end, but a transition. The material shed by our star will drift and mix with the interstellar medium, contributing to new clouds that will one day form new stars. The core that remains will spend eons cooling and dimming, quietly existing as a white dwarf, the retired shrunken form of the star that once was. Before we follow the core into its final quietude, there's one more grand spectacle to consider, but for that, we must turn our attention to those stars who lived faster and died more dramatically. Our star's death was serene and picturesque. For much more massive stars, the end is explosive and world-altering. In the next chapter, we will witness the grand finale of a massive star's life, a supernova, and the exotic remnants it leaves behind. Our sun's life ended in a gentle fade-out, but not all stars bow out so quietly. For the most massive stars in the cosmos, those perhaps 10 or more times the sun's mass, the finale is a spectacular blaze of glory, a supernova explosion that briefly outshines an entire galaxy. This is the grand finale of a great star's life, and it is both an ending and a cosmic renewal, forging elements and scattering them across space. Let's set the stage. A massive star, after burning through its core hydrogen in mere millions of years, continues to fuse heavier and heavier elements in a sort of frantic late-life career. After hydrogen is exhausted, helium fuses into carbon. When helium runs low, carbon fuses into neon, then neon into oxygen into silicon, and so on, each stage burning faster than the last as the core contracts and heats further. Layer by layer, the star builds up an onion-like structure. At the centre, a core of iron, about to form. Around it, concentric shells where different elements are undergoing fusion. Silicon outside the iron core, then oxygen, then neon, then carbon, helium, and an outermost shell of hydrogen still burning. By this point, the star has swollen into a red or blue supergiant and is millions of times more luminous than our sun, though its life at this stage is measured in mere hundreds or tens of thousands of years. Finally, the star's core becomes primarily iron, and iron is a dead end for fusion. Fusing iron into heavier elements consumes energy rather than releasing it. This is the equivalent of a car running out of gas. The engine sputters, and suddenly there is no pressure to support the star's immense weight. In literally a matter of seconds, the balance that has held the star up for millions of years is catastrophically broken. The iron core, about the size of Earth or smaller, collapses under gravity's onslaught. Protons and electrons in the core are crushed together into neutrons. The core becomes essentially one giant atomic nucleus, a ball of neutrons no bigger than a city. The collapse is so rapid and extreme that it's like watching an enormous building implode in the blink of an eye. When that neutron core forms, it is incredibly dense and stiff. Quantum forces between neutrons suddenly provide a huge pressure. The infalling material of the star slams into this hard surface and rebounds. Moreover, in the core collapse, a flood of neutrinos, ghostly subatomic particles, is unleashed from the core, carrying away an immense amount of energy. These processes launch a shockwave outward. In a few heartbeats, the shockwave tears through the star's layers, and the star explodes from the inside out. The outer layers, everything from the core boundary outward, are blasted into space at a significant fraction of the speed of light. The energy released in this moment is almost unfathomable. For a short time, the exploding star can radiate more energy than all the billions of other stars in its galaxy combined. The star that was once a brilliant beacon now becomes a supernova, climbing in brightness rapidly. If such a supernova occurs within, say, a few thousand light-years of Earth, it can be as bright as the full moon in our sky. In fact, humans throughout history have witnessed these guest stars. In July of the year 1054, Chinese astronomers recorded the sudden appearance of a new star so bright it was visible even in the daytime for over 3 weeks. This was the supernova that created what we now know as the Crab Nebula. The expanding cloud of debris from that long-ago explosion is still visible in telescopes today as a filigree of luminous gas. In 1572, the Danish astronomer Tycho Brahe was astonished to see a brilliant new star in the constellation Cassiopeia. We now call this Tycho's supernova. And in 1604, observers including Johannes Kepler documented another spectacular new star, Kepler's supernova, in Ophiuchus, which likewise shone brightly before fading. These events profoundly impacted astronomy. They proved that the heavens were not immutable and unchanging as once thought, but dynamic and occasionally unpredictable. In modern times, we haven't had a naked-eye supernova in our Milky Way galaxy since then, though supernova 1987A in a nearby galaxy, the Large Magellanic Cloud, was visible to the naked eye in the southern hemisphere. But we see supernovae in other galaxies with our telescopes on a regular basis, each one the brilliant death cry of a massive star. Now, as chaotic and violent as a supernova is, it is also a tremendous creative moment. In the fury of the explosion, the star's core may crush even further to become a neutron star, or if the star was extremely massive, a black hole. But we'll speak more of those in the next chapter. For now, consider the debris blasting outwards. The temperatures in the shock front are so high that they trigger fusion of elements far heavier than iron. Elements like gold, silver, uranium, rare and heavy atoms are forged in those split seconds of chaos and sewn into the expanding layers of gas. The supernova's remnants, its ejecta, therefore carry a rich assortment of the periodic table. When we marvel at a gold ring or the iodine in our salt, we are looking at atoms that may well have been formed in a supernova explosion eons before our solar system existed. The supernova is thus a cosmic forge, a final act of creation by a dying star, which seeds the next generations of stars and planets with the heavy elements that make rocky worlds and biology possible. As the supernova blast wave expands, it plows into the surrounding interstellar medium, sweeping it up into a shell and exciting it to glow. For centuries, the aftermath of the explosion remains visible as a supernova remnant, like the Crab Nebula, or the glowing filaments of Tycho's and Kepler's remnants that today we observe with X-ray and radio telescopes. These remnants are beautiful in their own way, tangled webs of gases enriched with stellar ashes, racing outward and mixing into space. Eventually, over tens of thousands of years, they will disperse and merge with the general interstellar gas. But their gifts, the elements, will remain, ready to become part of new stars, new planets, perhaps new living beings. In fact, our very solar system likely formed in part from the debris of long-ago supernovae. A subtle chemical fingerprint in meteorites tells us that one or more supernova shockwaves may have even triggered the collapse of the cloud that gave birth to the Sun. To witness a supernova from a safe distance is to witness both an ending and a beginning. A star's life in one brilliant flash gives way to a diffuse nebula and an extremely dense stellar remnant. The darkness that follows is not a cold oblivion, but rather the nursery for future suns. In the next chapter, we will linger a moment with the exotic objects left behind by such violent ends, the neutron stars and black holes, which are no less fascinating as echoes of gravity from the massive stars that once were. For now, let us take a mental step back and admire the concept. Somewhere in the galaxy, perhaps tonight, a massive star is ending its life in a supernova. If we are lucky, perhaps humanity will see one explode in our Milky Way again, lighting up our night with a brief second moon and reminding us in no uncertain terms of the dynamic, ever-changing nature of the universe. After a supernova fades, we are left with the cores of the once mighty stars, objects so strange and extreme that they defy our ordinary intuition. These remnants are essentially pure gravity and quantum physics made manifest, neutron stars and black holes. They are the echoes of a star's life, carrying its memory in their mass, spin and field long after the brilliant fireball of the supernova has expanded into space. Consider a neutron star first. This is the compressed core of a massive star that didn't quite have enough mass to become a black hole. Imagine something perhaps twice the mass of our Sun crammed into a sphere only about 20 kilometers, 12 miles, across, roughly the size of a city. On Earth, a sugar cube-sized piece of neutron star material would outweigh Mount Everest. The gravity on its surface is so immense that if you dropped a rock from a height of 1 meter, it would hit the surface in a microsecond and liberate as much energy as an atomic bomb. Neutron stars are made almost entirely of neutrons, packed together in a state of matter so dense we can scarcely imagine it. The word star seems almost inappropriate. It's more like a giant atomic nucleus, a stellar corpse left behind when the core of the star was crushed and the rest blown away. Many neutron stars announce their presence through extraordinary beams of energy. We call these ones pulsars, cosmic lighthouses that sweep beams of radio waves, light, or even X-rays across the sky as they spin. When the core collapsed, it conserved angular momentum, like a spinning ice skater pulling in her arms, so what was once a leisurely rotating star can become a rapidly spinning neutron star. Pulsars can spin anywhere from once every few seconds to hundreds of times per second. Indeed, the first pulsar discovered was jokingly nicknamed LGM-1, for Little Green Men 1, because its radio pulses were so regular and rapid that scientists half seriously wondered if they were signals from an alien civilization. But it was nature's doing, a rotating neutron star with a strong magnetic field that channels energetic particles into twin beams. When one of those beams sweeps past Earth, we detect a pulse. It's like hearing the steady tick of a fantastical cosmic clock. Some pulses are so stable in their rotation that their timing rivals atomic clocks in precision. Not all neutron stars pulse in our direction, but they all are incredible in other ways. A subset of neutron stars called magnetars possess magnetic fields 1,000 times stronger even than a typical neutron star, which is already trillions of times beyond Earth's magnetic field. These are the universe's most magnetized objects. A magnetar's magnetic field is so intense that at distances of tens of thousands of kilometers, it could distort the electron clouds of atoms. At closer range, it would erase the data on any credit card by sheer force. If one were to pass by Earth at half the distance of the Moon, it would wipe every credit card and electronic device clean, a rather unearthly thought. Magnetars occasionally unleash bursts of high-energy radiation when their intense fields cause starquakes in their crust, releasing more energy in a fraction of a second than the Sun does in a year. Thankfully, they are rare. Only a few dozen are known in our galaxy, and far from us. But they remind us that even in death, stars can exhibit spectacular behaviours. And then there are black holes, perhaps the most famous and infamous stellar remnants. If the core of a dying star is above a certain mass threshold, around 3 solar masses, not even neutron degeneracy pressure can halt the collapse. The core implodes to essentially a point of infinite density, as far as our physics can tell, a singularity, and an event horizon forms around it. The event horizon is the boundary around a black hole, beyond which not even light can escape the gravitational pull. It's not a physical surface, but rather a sphere of influence. Cross that boundary, and you're inevitably drawn into the centre. To the outside universe, that point of no return marks the surface of the black hole. Black holes truly earn their name. Within the event horizon, all light is trapped, and thus the hole appears black. But black holes are anything but nothingness. They have mass, often angular momentum, and possibly electric charge. They distort space-time around them, causing effects we can observe. One such effect is gravitational lensing, the way a black hole, or any massive object, bends the path of light. If a black hole passes in front of a distant star or galaxy, it can act like a lens, creating halo-like rings or multiple images of the background object. We've even imaged the shadow of a black hole in recent years, the famous silhouette of the supermassive black hole in galaxy M87, and the one in the centre of our Milky Way. These images show a dark circle, the event horizon's shadow, surrounded by a ring of light. The glowing gas just outside the event horizon, heated to extreme temperatures as it spirals inward. It's an almost poetic confirmation of what general relativity had predicted, that gravity can twist light and darkness into strange new shapes. While neutron stars are, in a sense, the last stable configuration of matter, black holes represent a true collapse to nature's ultimate abyss. And yet, modern physics suggests that even black holes might not be completely black forever. In the 1970s, Stephen Hawking proposed that black holes can slowly evaporate via what's now called Hawking radiation, a very weak emission of particles due to quantum effects near the event horizon. For an asteroid mass black hole, this evaporation might be quick, but for a stellar mass or larger black hole, it's incredibly slow, far longer than the current age of the universe. Still, the idea is profound. Given enough time, trillions upon trillions of years, even black holes may fade away, returning their mass energy to the universe in the form of subtle radiation. In the end, even these darkest of star ghosts are not eternal. At this point, we have followed the journey of stars from birth to death to aftermath. Our once normal star became a white dwarf and will cool into obscurity. A more massive star became a neutron star or maybe a black hole, cosmic monuments that slowly change over eons. And we find ourselves reflecting on the grand cosmic cycle. Stars are born from the ashes of previous generations, and when they die, they enrich and shape the space around them for new stars to come. The music of the spheres, a term ancient philosophers used to describe the cosmic order, has taken on a new meaning today. We literally transform astronomical data, like pulsar signals or gravitational wave detections, into audible sound to better analyse them, letting us hear the universe's rhythm. In the final chapter, we will touch on this idea and the ways we are now listening to the cosmos, adding a new sense to our exploration. Hearing the light, the vibrations, the gravitational waves, a fitting coda to our gentle journey through the life of a star. Throughout our journey, we've often used visual and tactile imagery to imagine the life of a star. But there's a hidden soundtrack to the cosmos as well, one that we're only beginning to appreciate. Ancient philosophers spoke of the music of the spheres, the idea that the movements of celestial bodies form a kind of harmony, a music too refined for our ears. Today, in a beautiful twist, we are literally converting astronomical data into sound, allowing us to listen to the universe's silent melodies through a process called data sonification. In these final moments of our exploration, let's gently tune our ears to the cosmos. Consider, for instance, the merger of two black holes. Such an event is utterly dark. No light escapes those colliding horizons, but it is far from silent. When two massive black holes spiral together and merge, they send out ripples in space-time, gravitational waves. In 2015, scientists using the LIGO detector in the US heard these waves for the first time as they passed through Earth, very slightly stretching and squeezing the detector's arms. After sophisticated filtering, the signal they found could be converted into a sound. What did it sound like? A brief chirp, a rising tone that lasted just a fraction of a second, as the two black holes, each about 30 times the mass of the Sun, whirled faster and faster and then coalesced. That little chirp, almost like a bird's tweet or a dropping pebble's plink, was the voice of an event that released more energy in an instant than the light of all the stars in the observable universe combined for that instant. It was the music of pure gravity, rendered audible. We have since detected many such chirps from distant collisions of black holes and neutron stars, each one a fleeting note in the cosmic symphony, telling us about the masses and spins of these hidden dancers. The universe has other songs too. In the realm of light, we can take data, say, the brightness of an object over time, or the frequencies of light in a nebula, and map it to sound. A complex image, like the majestic remnant of a supernova, or the swirling gas of a galaxy, can be sonified by scanning across it and assigning musical pitches to the intensity or colour of the light. The result might be an eerie, wave-like hum, or a series of string-like notes that rise and fall, a direct translation of starlight into sound. These techniques not only create hauntingly beautiful audio experiences, but also offer new ways to discern patterns in the data, perhaps revealing subtle variations that our eyes might miss. One very poignant example of cosmic sound is the cosmic microwave background, the afterglow of the Big Bang itself. This light, now stretched to microwave frequencies by the expansion of the universe, is a snapshot of the universe when it was only 380,000 years old. But it also encodes primordial sound waves. In the hot plasma of the early universe, pressure waves, effectively sound, rippled through the dense mix of light and matter. When the universe cooled and expanded, those sound waves left imprints in the cosmic microwave background. Scientists have taken that data and shifted it upwards in frequency, since the original notes are far too low for human hearing, to produce a representation of the sound of the early universe. What we hear is a kind of gentle hiss or hum, punctuated by a broad rising and falling tone, the reverberation of creation, so to speak. In truth, it's more a texture than a melody, but it is remarkable to think that we can, in a way, listen to the echo of the Big Bang's afterglow. We are effectively hearing the oldest sound in the universe, transposed for our ears. Closer to home, even the planets and moons have their voices. The magnetosphere of Earth sings with radio waves that, when converted to audio, sound like chirping birds at dawn. The Cassini spacecraft, when it crossed through Saturn's rings, recorded dust particle impacts that sounded like clicks and pops increasing in intensity. Jupiter's ionosphere emits whistling and whooshing radio bursts that, when played through a speaker, truly sound like alien winds and surf. All these are naturally generated sounds of electromagnetic vibrations or particle hits that we've shifted into audible range. In a more poetic vein, one might say that by turning astronomy into music, we are finding a new way to connect our senses to the universe. Each star, each galaxy, each black hole might be interpreted as a unique instrument in a grand cosmic orchestra. We've long appreciated the visual beauty of the heavens. Now we are beginning to appreciate its aural beauty. The high, rapid tick of a pulsar, the deep roar of a black hole merger, the whispering static of the cosmic background, these are nature's songs. As our journey through the life of a star comes to its end, we find ourselves reflecting on the unity of it all. The atoms that made our star and its planets were forged in prior stars and dispersed by prior supernova. Our star's gentle life and peaceful death, in the case of a sun-like star, or spectacular death, in the case of a massive star, sows the seeds for new stars to come. We ourselves, in body and in spirit, are connected to this cycle. We are made of star stuff, as Carl Sagan famously said. The carbon in our cells, the calcium in our bones, the iron in our blood were all forged in stellar furnaces or during supernova explosions long before Earth existed. And through our curiosity and intellect, we've found ways to read the light of stars, to touch them with robotic probes, stardust collected by spacecraft, and now even to hear their silent music. In the quiet of your room or wherever you are, take a moment to appreciate that connection. Over the course of this gentle journey, we have travelled from the star's birth in a cosmic cloud, through its long sunny days of adulthood, into its expansive glow of old age, and finally to its transforming farewell. It's a story that spans millions to billions of years, yet it's also the story written in every atom of our bodies. When you next gaze up at the night sky, perhaps you'll remember that each star up there is singing a story of creation, endurance, and transformation, even if our ears can't hear it directly. Now, dear listener, it's time to drift into your own quiet space. As you close your eyes and breathe softly, imagine the lullaby of the cosmos surrounding you, the hush of the interstellar clouds, the distant choir of starlight, the faint ringing of cosmic rays hitting Earth's magnetic field. Feel the bond between you and the stars. We are children of the stars, listeners of their light, and now, perhaps, attuned to their subtle music. Sleep well and dream of the stars, the gentle, eternal companions watching over us from the darkness, singing their ageless song.